So by definition, it is the study of the interaction between matter and electromagnetic radiation. So we're basically giving matter electromagnetic radiation, and then we're observing what happens as a result. Are things emitted, absorbed, reflected? And then we analyze those results, and using those results, we can draw conclusions about a sample structure, identity, phases, strain, different properties like that. And there are many different methods, and we've come a long way since the beginning of spectroscopy. At the beginning, we basically had some visible light and maybe a prism, and then we could split the visible light into a spectrum. And now we've come all the way to nuclear magnetic resonance spectroscopy. This is the NMR spectroscopy for ethanol, and we can see how the different hydrogen are bonded in the ethanol molecule. And like I said, there are many different methods. There's X-ray diffraction, X-ray reflectometry, X-ray fluorescence, X-ray photoelectron spectroscopy, nuclear magnetic resonance, and even more than that. So moving on, we'll talk about the structure of the atom. So we probably all remember from physics class, the atom has protons, neutrons, and electrons. Protons and neutrons are in the nucleus, and electrons are in the electron cloud orbiting the nucleus. And protons have a positive charge, neutrons have no charge, and electrons have a negative charge. And then the atomic number of an atom is equal to its number of protons. And for each element, there is a different number of protons. Then electrons outside the nucleus are participating in bonding. So if they are shared, we have covalent bonding. If they're exchanged, we have ionic bonding. If they're free to kind of move, we have metallic bonding. And each electron has 4 quantum numbers. Its principal quantum number, its angular momentum, its magnetic and spin quantum number. And this is kind of like the social security number of an electron. They are, every electron in an atom has a different set of quantum numbers. The principal quantum number was kind of introduced by Niels Bohr, and that quantum number describes what energy level or orbital the electron lies in. The angular momentum and magnetic quantum number were introduced by Arnold Sommerfeld, and those two describe the shape and the orientation of the orbital, the space that the electron could be. And then the spin quantum number is a little more complicated, and we will get into that momentarily. But all of these elementary particles, protons, neutrons, and electrons, all have spin. So then we might also wonder what these elementary particles are even made up of, and they're made up of quarks. And so quarks are responsible for many different interactions and forces. They're responsible for the strong nuclear force. An exchange of particles between quarks is responsible for the strong nuclear force, which keeps atoms together. And quarks, like the protons and the electrons, have a charge, and then like all of them, they have spin. And so if we look at the charge specifically on quarks within these particles, we can kind of actually see, why a proton has a positive charge. A proton has 2 up quarks, and they have a charge of positive 2/3, and they have 1 down quark, which has a charge of negative 1/3. And so if we add these together, the net charge on the proton is a positive 1/3, which makes sense because protons are charged positively. And then the neutron has 2 down quarks and only 1 up quark. And this also makes sense because with only 1 up quark, which has a positive 2/3, and then 2 down quarks and negative 1/3, those two can combine, and the net charge on the neutron is nothing, which that all adds up. And so quarks all have charge, and then quarks also have spin. And so now let's talk about what even is spin. So it's important when talking about spin to talk about some of the experiments that kind of help make spin make more sense. So the first experiment that kind of highlighted spin was the Stern-Gerlach experiment in 1922. And Stern and Gerlach, they sent a beam of silver ions through a magnetic field, and then they detected their results on a detector screen. And they wanted to see how the beam would interact with the magnetic field. And they hypothesized that one of 2 things would happen. Either the beam wouldn't interact with the magnetic field at all, and that they would just get like a singular dot on their detector screen, right where the beam was shot, or they thought that it would interact with the magnetic field and that the ions would act like small metal balls, but they would get like a spattering on their detector screen. But what they got was neither of those 2 things. They got a like 2 distinct lines above and below the like where the beam was aimed. So, and that was later attributed to spin. That was why that happened. And so then later in 1925, Uhlenbeck and Goldschmidt were working on, they were studying the Zeeman effect, and the Zeeman effect was discovered by Peter Zeeman, named for him, in 1896, and he observed the splitting of spectral lines during the n=3 to n=2 emission of hydrogen in the presence of an external magnetic field. So he boosted those electrons to a higher energy level, and then he let them fall and emit a photon, and then he looked at the resulting spectrum, and he tested it without a magnetic field, and we just had, you know, one regular spectral line, but then he did it with a magnetic field, and the line split into 3. And so that effect was named the Zeeman effect, and Uhlenbeck and Goldschmidt were studying that effect, and they hypothesized that the Zeeman effect was a result of an intrinsic property of particles, that they had intrinsic angular momentum, which gave them these magnetic properties. So the results of these hypotheses and experiments is that we have this property called spin, and it's intrinsic angular momentum. But these particles aren't actually spinning; they just behave like they do. And for particles, there are 2 spin states. For like an electron, you could have plus a half spin or minus a half spin. And most of these experiments were specific to electrons, but it's not only electrons that have spin. Protons and neutrons also have spin. So this was like a lot of information, but we know 2 things. We know that the particles have intrinsic angular momentum that we've called spin, and we know that they exhibit magnetic properties because of this spin. But how is that possible? Why does the spin give the particles magnetic properties? Well, for that, we're gonna have to talk about magnetic fields. And so we probably all remember from maybe physics class that when a charged particle is moving, it will generate a magnetic field. And this is actually due to special relativity. So in order to make this make more sense, I am going to give a situation, an example. So imagine that you're sitting at a desk and you have an infinite neutral wire stretching out infinitely in both directions, and the current is flowing to the left. You have negative charges flowing to the left, and you have positive charges, obviously, to the right. And then you've placed just one electron near the wire. For the sake of this example, imagine you can see charges and electrons. So in this case, you know, the charges are flowing, but every point along the wire, the charges are balanced, it's neutral. So the electron should not move, it should stay exactly the same where it is. But now if we change reference frames, if we kind of imagine that we're now in a car and we're driving to the right past the wire along that line, we're driving to the right, what's going to happen is the negative flow of electrons going the opposite direction is going to appear length contracted, and the positive flow is going to appear length elongated. And how I like to think of this is if I'm on the highway and I'm driving, and if I was a bad driver and I looked behind me, the cars that were zooming past me in the other direction they're going much faster than me relative to me. They're going much faster. And so when I look behind me, I'm not going to be able to really see the spaces between the cars. They're all going to be kind of bunched up. And then if I look ahead of me, all the cars going in the same direction as me, they're going a slower speed relative to me. And so I'm going to be able to see the spaces between the cars. I'm going to see each individual car as it stretches out ahead of me. And so that's kind of what I imagine this as. So if we look at this, right, the negative charges are going to appear bunched up on one side and the positive charges are going to appear bunched up on the other. And if we have this, we have a difference in charge. So then it appears that the electron should be accelerating to the right because it will be attracted by the positive and repelled by the negative. But how is this possible? Both reference frames are valid. We can't just change reference frames and just break physics. We can't do that. According to the lab reference frame, the desk reference frame, the electron shouldn't move. All the points along the wire are neutral, so it shouldn't move. But then according to the car reference frame, there is a difference in charge and the electron should feel in that force. The answer, in order to not break physics, is that the charge actually has to be in motion to exhibit these properties dubbed magnetic properties, because relative, if you're driving in that car past that electron, relative to you, the electron is moving. So that's why it will feel some magnetic force. So why is this even important? Well, if we know our two things, we know that the particles are charged and they have this intrinsic angular momentum, and we know that moving charges generate magnetic fields. We kind of smush those ideas together. We know that if a particle exhibits intrinsic angular momentum and it has a charge, it acts like it's spinning, so it can act like a charge carrying loop. And if the charge is moving, it will generate a magnetic field. So particles can be modeled kind of as tiny bar magnets. So they have a magnetic moment, they have a magnetic moment vector. And it's really easy to understand why protons and electrons exhibit these properties, because they have a charge, they have a spin, boom. But neutrons, they don't have a charge, but they also have a magnetic moment vector. And this is due to the charge and spin on the quarks within the neutron. So it's not as intuitive, but neutrons still have a magnetic moment vector. So of course, you're probably wondering what this even has to do with NMR. We have to, when talking about NMR, it's called nuclear magnetic resonance. So we're going to talk about a nucleus. And there are some differences when moving from one particle to an entire nucleus. So here I have this table, and on this side, we have nucleons, which are protons and neutrons, and then electrons in their own columns. And then we have a nucleus in its own column. Nucleons and electrons have one magnetic moment vector. It's simple. But then a nucleus has a net magnetic moment vector. There are multiple particles within a nucleus, so they're all going to be going in different directions, and either they'll be canceling each other out or they'll be adding together. So a nucleus will have a net magnetic moment vector. And then I have the values for the magnitude of the magnetic moment vector. For nucleons, I have the magnitude of the neutron's magnetic moment vector over the magnitude of the proton's magnetic moment vector. And what this value implies is that the proton's magnitude of its magnetic moment vector is greater than the neutron. And this is due to, since protons and neutrons weigh the same amount, they have the same mass. This is due to the difference in charge, because the magnitude of this vector depends on the charge, the charge to mass ratio of the particle. And so it's due to the difference in charge that these are not the same value. And then electrons, their magnitude of their magnetic moment vector is close to negative 9.3 times 10 to the negative 24th joules per Tesla. And then the nucleus, there's no set value, because we have different nuclei with different numbers of protons and neutrons. So there's no set value, but in the case of NMR, we're looking for a nucleus that has a non-zero spin quantum number. And I'll talk more about why we need that momentarily, but we need a nucleus that has a non-zero spin quantum number. And there can be more than two spin states for that nucleus. So then, like I said, in a nucleon, they just exhibit intrinsic magnetic properties, and they're within the nucleus. Electrons, they do have a magnetic moment vector, so they do play a role in NMR, even though we're talking about a nucleus. And so that's why we have this concept, nuclear shielding and de-shielding. But that's beyond the scope of this presentation, because that's what my next presentation is on. And then the nucleus, like I said, it's a nuclear magnetic resonance. It's the basis for NMR. And so when we apply an external magnetic field to certain nuclei, the magnetic moment vectors, the nuclei are going to align depending on its spin, on the nucleus's spin. It will align and create different energy states, which is the basis for NMR. So now I'll talk about the number of nucleons. This table is taken from the University of Michigan, and this is a list of some useful isotopes, some useful elements that we may use in NMR. And so the odd number, when you have an odd number of neutrons and an odd number of protons, these are some examples, I've highlighted them. Hydrogen 2, 1 neutron, 1 proton. When the nucleus has an odd number of neutrons and an odd number of protons, they'll have an integer spin. So 1, 2, 3. Hydrogen 2 has a spin of 1. Boron 10 has a spin of 3. And hydrogen 1 technically falls into this category, except that it doesn't have any neutrons. So it's a little bit of an exception. It has a spin of a half. And then the next category is an even-odd mix, like an odd number of neutrons and even number of protons, or vice versa. And these are much more common. The odd numbers of both are more rare. but the even odd mix is much more common. And I've also added hydrogen 3, which is tritium, and it is extremely rare in nature. It has a half spin, and it is radioactive. It's unstable. And as you may notice, the even odd mix will have an half integer spin. So 1/2, 3/2, 5/2. And then finally, I've added a good example of one that has an even number of both. And when you have an even number of both protons and neutrons, you'll have 0 spin, which is very unfortunate for us trying to do NMR, because carbon-12 in this example is 98.93% abundant in nature, but it's not useful for NMR. It has 0 spin. And I'll talk more about why it's not useful momentarily. But the isotope we can use is carbon-13, but it's only 1.1% abundant in nature, which is pretty unfortunate. But that's one weakness of NMR. But one strength of NMR is when we can use hydrogen, because the isotope of hydrogen that's useful is 99.98% abundant. And the other, hydrogen 2 is also useful, but it's not as abundant. But this is very useful for doing NMR spectroscopy on polymers, because polymers have a lot of hydrogen. So this is one excellent strength of NMR, that we can do NMR on polymers. They have a lot of hydrogen. So why do we need why do we need a non-zero spin? Well, like I said before, when we don't have a magnetic field, the nuclei have magnetic moment vectors, but there's no energy difference. They're all just there. But when we apply a magnetic field, the magnetic moment vectors will all align. Depending on their spin, they'll all align, and there will be this energy difference. There will be a higher energy state and a lower energy state depending on how they align. And then that energy difference is kind of where we start with NMR. And so the number of spin states can actually be determined by this equation, 2i + 1, I being the number of spin states. And so if we look back at carbon-12, we can put its spin into the equation. 2i + 1 equals number of spin states. 2 times 0 + 1 equals 1 spin state. If we only have 1 spin state, then we have basically this situation right here, and there's no energy difference like here. We need this energy difference, and that's why we need a non-zero we need a non-zero spin. So, and that's just the beginning. There's much more beyond this energy difference, but that will be covered in a later presentation. So today I talked about spectroscopy, what it is, some of the different types. We talked about protons, neutrons, and electrons, and why those are important. They're different properties. Talked about spin and special relativity, why spin gives these particles magnetic properties. I talked about the magnetic moment vectors within both particles and the nucleus, and then we talked about how that magnetic moment vector changes when the atomic particles are in the nucleus, and why it's important for NMR. So in the future, today I talked about spectroscopy, atoms, and spin, but next time I'll talk about nuclear shielding and deshielding, and then chemical equivalence, and that'll be on July 13th. So thank you. Any questions?
Thank you, Porter.